Okay, so this is a Maths 1A request session, and these are the requests I've had: eigenvectors, domain and range, including inverses, and trig substitution. I may start with the domain and range first. Domain and range is one of those things that the lecturer will often not expect you to show very much working for. You're allowed to just sort of state it most of the time, because it's not actually a very easy thing to do. Well, range is hard. Domain is easier than range. And so the definition of domain, the domain of a function is the set of input values that are meaningful, okay, that you're allowed to use. So the sometimes the domain is declared to begin with, and it says the domain is from minus pi to pi, okay, and you're just told what the domain is. Because a function, in completely technical sense, sin x is not enough information for me for a mathematician to figure out what the function is. Because a function doesn't just have a formula, it sometimes doesn't have a formula at all, but it doesn't just have a formula, a rule for deciding which x goes with which y. It also has a domain which tells you which x's you're allowed to use. Okay, but sometimes, being lazy, as mathematicians are, if someone does not specify what the domain is, then you're allowed to use all the possible x's that make sense. Okay? All of the ones that anyone is allowed to use ever. That is the domain. And the range is the output values. All of them. So if you use all of the input values that you're allowed to use and you collect together all of the matching output values, and that collection together, that is the range. So that's the domain and the range. So finding domains is often easier than finding ranges, especially in the sense where they've just told you what the domain is there already. So that's the domain. Yay. But it's usually just having a think about what you're allowed to use in your function. Okay? So the domain and range of 1 over root x squared minus 3. So technically when they say the domain, they really should say the largest possible domain. Okay, because when a mathematician defines a function, they're supposed to tell you the domain in advance, but this is one of those times where we're a bit sloppy. So the largest possible domain. So what is the biggest possible set of x's for which that function makes sense? And we're always assuming that my function is a real valued function, and we're not having complex answers. This is just for real valued functions. If they wanted complex numbers, they would explicitly say so. But complex numbers only appear twice in first year maths. And you've seen them in eigenvalues, so it's not going to be here. So I want to know what the domain is. So first I'll think about the domain. And the domain is all of the x's for which that makes sense. So I want to know, when is that defined? So there's two approaches. You can say it's defined for these x's, and then that's the domain. Or you can say it's undefined for these x's, and the domain is everything else. And whichever way you want to go about it is fine with whoever's reading it. So we're going to investigate. We're going to have a quick look at it, and we're going to investigate what is it that might cause this function to not be calculable. So we have the root's going to be a problem. If whatever's under that root sign is less than 0, I'm not going to be able to produce a real number answer. And so that's my first clue. Anything that's inside there has to be positive in order to work. And also this division is the problem. The bottom of a division isn't allowed to be 0 either. And so I can't have the whole answer from this being 0. So because of the root, because of all of that reasoning, we need... So the first bit of reasoning is we need that this is not allowed to be 0, because it's on the bottom of a fraction. And we also need x squared minus 3 to be positive. Well, at least not, it's not allowed to, because the root has to be defined. Now, since the root isn't allowed to be 0 and the x squared minus 3 is allowed to be greater than or equal to 0, so what we actually need combining them together is that this has to be strictly greater than 0. So I need x squared to be strictly greater than 3. Awesome. So when I do the square root of both sides, I will get mod x is strictly greater than root 3. So there are many ways of dealing with inequalities that have quadratic equations in them, and this is one of them. If you can arrange it to get x squared greater than or x squared less than, when you square root the x squared, it becomes a mod x, because you know that the square root of minus 3 squared would be plus 3, which is mod minus 3. So the square root of x squared is mod x. So you need the size of the number x to be more than root 3. So let me just draw a diagram of that. Here is root 3, and all these numbers have a size greater than root 3. But here is minus root 3, and all of these numbers have a size greater than minus root 3, greater than root 3 as well. So when you have an x squared greater than, and you do the square root, you'll get the outside, just here. So we're going to get, that is, x is greater than root 3, or x is less than minus root 3. There is another way of dealing with that if you want to put an extra bit of working in. Let me show you. Are you ready? Mod x is plus or minus x. Could be plus x, could be minus x, depending on what x is. So we get plus or minus x is greater than root 3. So we either get plus x is greater than root 3 or minus x is greater than root 3, which is x is less than minus root 3. Yay! And so those are my two answers. So it turns out that this is the diagram I'm looking for. I'm not allowed to be actually equal to root 3. And so I've got that the domain of f is from minus infinity to minus root 3, and also from root 3 to infinity. And that's how we write it in interval notation. Everything from here up to root 3, minus root 3, and also everything from root 3 to infinity. That is the domain. It's made of two pieces that I've glued together with my union symbol. Okay, that's domain. The range, is a whole different story. If you're handy with a graphics calculator, you can always get it to draw it for you. But sometimes that can be a little bit misleading because the graphics calculator only shows you like this much of the function. So you have to fiddle around with the view windows to really see what's going on there. And the other thing with range is to ask yourself for questions about what numbers could come out of your function. That's how to ask about ranges. And so the range is the list of all the output values. So what comes out of my function? So I need to ask myself, can I make 0? That's the most important number to ask. So let's look at my function. Is it possible to produce 0 as an answer from that function? Got a clue for you. Just give you a couple more seconds. Clue is that it's impossible to produce 0 by division unless there's a 0 on the top. Number that is not 0 divided by another number that is not 0 cannot be 0. That's impossible. So 1 divided by some number, and you know that that number can't be 0 because it's on the bottom of a fraction. 1 divided by some non-zero number cannot possibly be 0. That's impossible. And so therefore, no, it's not possible because it's produced by a 1 over. 1 over anything can never be 0, and that's a very useful thing to know. Nope, can't produce 0. Can, and the next question is I'm going to restrict myself down to the positive numbers and the negative numbers and ask myself what I can make. So can I make negative numbers? Can I make negative numbers out of that function? I've got at least one person shaking their head. The answer is no, I can't. Because root, when I write root something, I'm explicitly saying it's the positive one. The only way you can possibly have a minus out of a root is when you explicitly say it's plus or minus. And so this function is root something, and so no, I can't because of the root. Can I make positive numbers? Well, yes, I can make positive numbers. So my next question is, so I can't make 0, I can't make negative numbers, I can make positive numbers generally. Which positive numbers can I make? Is there a minimum possible positive number I could make? Is there a maximum possible positive number I could make? So, well, let me say, is there a maximum? Is there an upper limit to the size that this could possibly be? Got a couple of people saying no, and that's right. 1 over anything, as long as you're allowed to make that anything as small as you want, you could make the 1 over anything as big as you want. So there's no maximum. You know, is there a maximum? Nope, no maximum. As big as you want. Okay? Because I can make x squared really, really close to root 3. And so, like, you know, I can make x squared 3.0001, and I'll get 1 over 0.001, and I do 1 over that, and I get a huge number, like 1 million or so. Okay, and so I can make as big as I want. Is there a minimum number? So think about what happens. So what we've done to make our big number, we had to make x really small. Okay, we had to make x close to root 3. So we chose the small end of the x's to make the answer bigger. So we should try the really big x's. What happens if x is super huge? I've got something. Someone be brave enough to say it loudly. If x is like 2 million, how big's my answer going to be? Really small. So I can make, if I make x big enough, I can make this total answer as small as I like. Is there a minimum? No. As close to 0 as I like. Okay, so it looks like my range, I'm allowed to go all the way up to 0 but not actually equal to 0, and I can go as big as I want. Now that reasoning sometimes leaves gaps in the middle that you haven't considered, but it's usually pretty good for the sorts of things they put in exams. Yeah, there you go. Okay, so things that are division have the tendency to cover everything from sort of 0 up. Okay, so then someone said, what about the domains and ranges of inverse functions? Okay, well, that's a bit curly. Domain and ranges of inverse functions are to do with the ranges and domains of their original functions. But have you got a specific example in mind there? No? Okay. Or, that loop. Okay, so this is my function. I've got x squared plus 2x plus 5 for x greater than or equal to minus 1. So that's my domain. I mean, technically the statement x is greater than or equal to minus 1 is not the domain. It's just a description of the domain. The domain is this, the domain of f is the set of x's such that x is greater than or equal to minus 1. So the statement x is greater than or equal to minus 1 is technically not a domain. It's just a statement that I could say aloud. The domain has to be a set. Really hoping I've actually chosen a domain that works. Yes. Okay. So the first step, and what I'm going to actually say, by the way, so that was just sort of useful information. So find F inverse including domain and range. Okay. So, if I'm going to find the domain and range of the inverse function, I need the domain and range of the original function. I have the domain of the original function, I now need the range of the original function. So I need to ask myself, that function there, what is its range? So I'll ask myself the questions again. Can I make 0? Can I? Can I make 0 out of that function, f of x? I might. It's possible. I think the answer is actually no. How can you tell if a quadratic function can make 0?
Consider the value of b squared take 4ac.
Ah, that's interesting. Consider the value of b squared take 4ac. So we could basically, that's like the quadratic formula. Okay, so we need to leverage what we know about quadratic functions. So we can attempt to solve it. Okay, solve it equal to 0. That'll tell us whether it's 0. We'll also, but technically I need more information than that. I need to know what the minimum is, I need to know what the maximum is. So what we are expected to for the range here is to know something about what these sorts of functions look like. Okay, this sort of function, it's a parabola. I'm going to draw a sketch of my function. I know it's a parabola and I know it's facing upwards. I don't know where it is yet, but I do know, at the very least, it goes up like that. That's my first pass at a sketch. So definitely this function ought to be able to produce any number high enough. Okay, my function goes upwards. I should be able to produce any big number because it's a parabola that faces up. And there must be a minimum somewhere. Okay, there will be a minimum possible value that it will produce. Okay, I need to figure out where that minimum is. So where is the turning point of a parabola? It's a great question. When the derivative is 0. Okay, so f dash x 2x plus 2, which is 0 when 2x equals minus 2 when x is equal to minus 1. Okay, so this turning point at x equals minus 1, so that's where the minimum occurs. How convenient, the domain was x is greater than or equal to minus 1. That's nice to know. Okay, and so my function is actually more like this. I'm going to get an updated sketch. I don't know where it crosses the axis. Just a second, let me figure out how high it is at that point before I update my sketch. So let's see, when x is equal to minus 1, we get f of minus 1 is minus 1 squared plus 2 times minus 1 plus 5, which is 1 minus 2 plus 5, which is 4. Awesome. That's what the y value is when x is minus 1. And so now I can update my sketch. This point here, oh, sorry, the y-axis is here, is minus 1, 4. That's what that point is there. And in fact, I was only allowed to use the bit where x is greater than or equal to 1. So I'm not using that bit at all. So that's what my function actually looks like. It has a minimum of 4. No, it can't be 0 because the minimum is 4. Okay, so what I actually have is that the range of f is actually from 4 upwards. So be aware that sometimes they're going to expect you to just have knowledge of how functions behave in order to figure out what the range is. So now, that's good. We have, I'm just going to do, it's the story so far. The domain of f is from -1 to infinity, and the range of f is from 4 to infinity. So that means that whatever the inverse is, its domain and range will be the other way around. The domain of the inverse is the range of the original function. The range of the original function is the domain of the inverse. Okay? This function takes numbers from -1 to infinity and produces numbers from 4 to infinity, and the inverse will do the opposite. It will take numbers from 4 to infinity and produce the numbers from -1 to infinity. Because the inverse function is supposed to do the opposite. It's supposed to come back again. So, I will just put in the bit where I figure out what the inverse is, but I do know now. So, the domain of f inverse will be the range of f, and the range of f inverse will be the domain of f. They'll switch over in the inverse. The picture in my head is that -1 to infinity via f produces 4 infinity, and f inverse comes back the other way. That's my little diagram of how I do it. So this is the domain of f and it produces this range. This is the domain of f inverse, it produces this range. And then the actual inverse, just while we're at it, even though it's not what we're asking for, but I might as well complete it. So let y be equal to f inverse x. That's how I always start finding an inverse. Some people like to start with y equals f of x. I like to switch the x's and the y's to begin with, because my goal is to figure out a formula for f inverse. So then I'll do f of y equals x. And the other reason I do this is because it matches with what I do for the derivatives of inverses. And then I don't have to remember doing two different things. So x is equal to... So let's see. F of y is what I get when I put y into the formula for f. So that is y squared plus 2y plus 5 equals x. So I didn't change the x, but I put y into the formula for f. And then my goal is to get y equals, because I need I need the formula for f inverse, which is what y is. So y, okay, interesting. I should attempt to either complete the square or use the quadratic formula. Because if x was a number, like say 3, I get y squared plus 2y plus 3, and you could conceivably attempt to factorize that, but since we have to attempt to factorize it for every possible x, we're going to have to use a method that won't require me to just think about what the factors are. So I have to use either completing the square or quadratic formula. Completing the square is probably illustrative, so I might do that. So let's see. Let me just make some space. I've moved the 5 over the other side. And I want this to be y plus something squared. So if I expanded this out, it would be y squared plus 2 times whatever was here times y plus whatever was here squared. And so therefore, this must be 1 because it's half of the 2y. Okay, completing the square means that I have to divide that bit by 2. And then if I do expand out the y plus 1 squared, it'll be y squared plus 2y plus 1. Only just a second, I can't just go adding a plus 1 randomly in the middle of nowhere. That would change everything, so I'll have to subtract the 1 as well. I know that the majority of you will have put the 1 over here, but I like putting it here for situations where there is no equal sign. So the y squared plus 2y plus 1 will be equal to this, and that will go over there to be an x minus 6, plus, no, minus 4. Is that right? Yep. And so I'm going to get y plus 1 is equal to plus or minus root x minus 4. Now it can't be both plus and minus, it can only be one, or it's not really a function, and so I'm going to need to figure out whether it's the plus or the minus. Let me just make it y equals so that I can figure that out. Okay, so this y is in the range of the inverse, and so therefore it's supposed to be in this set here, because y was f inverse of x. So it's in the range of the inverse, and the inverse goes from minus 1 up. So I have to choose the plus, so it goes from minus 1 plus a bit, so that it goes upwards. So since y is in the range which is from minus 1 to infinity. And so therefore f inverse x is actually minus 1 plus root x minus 4, with the domain of f inverse being 4 to infinity and the range of f inverse being minus 1 to infinity. And that's the final answer for that question. Now, that'll do for that, I think. So that was both sort of domain and ranges and finding inverses in when it's a little bit tricky. Now, I probably do not have time to do both eigenthings and trig substitution, but I would like to point out that there are any number of videos on my website about trig substitution. And as much as everyone would love me to do that, well, we could take a vote, but yeah, let's take a vote. Eigenthings or trig substitution. All right, trig substitution it is. I'll see how I go. I might just keep going. Okay. So is anyone brave enough to sort of try and articulate what it is about trig substitution that's the thing that worries you? Everything.
When to substitute what?
When to substitute what? Okay, that's a good thing to be worried about. Yep. Yep, knowing which identity to use, which I believe is the same thing, so that's good. So some people think about it in terms of trig identities, and some people think about it as when to substitute what, and it's good to be able to know which one works best for you. And then, of course, there's just a whole lot of stuff that you have to do along the way, I imagine. When you think about trig substitution, my instinct is that you see your life extending before you, and quite a lot of it is doing trig substitution. That's probably how you feel. It is long, and there is nothing we can do about that. I mean, the point of trig substitution is to make the integral possible, not to make it easy. Because possible is technically easier than impossible. So that's the idea of trig substitution. The actual whole point is to get rid of an annoying square root. Okay, by using a trig identity that will turn the bit that you want into a single square. So, I'm going to try and think of an example that will not turn to worlds of pain. Does anyone have a particular example that they've been worried about, that they're from an exam or something that I could take, or I would just do a new one?
2x on 1 take, square root of 1 take x to the 4?
Of course. Okay, so this may look like a trig substitution, but it's not. So this is the first double bluff, okay? So it looks like a trig substitution, but you know there's a list of things you should try before you try trig substitution. So the first thing you should try is you should look at it and see if you can do it. No, okay, worth a try. And then you should attempt to rewrite it somehow. So maybe expanding something out or factorising it. Yeah, roots just don't do that. Okay, so we can't do that. And then the next thing would be to try ordinary substitution. Well, that would mean that I would choose something that's inside something else in the hope that its derivative was sort of nearly there. Okay, the derivative was there, but possibly with the wrong constant. That's when ordinary substitution is most helpful. Well, the derivative of what's under the root sign is like 4x cubed. We don't have an x cubed, so that doesn't seem reasonable. Are there any other integrals I know that have a 1 over 1 minus something? Yes! Arcsine. Arcsine has a derivative that goes 1 over 1 minus x squared. Now I don't have an x squared, I've got an x to the 4, but that's okay, because it's just x squared squared. So this is sweet, because now the 2x is the derivative of the x squared. Awesome! So now I can just do ordinary substitution. Let u be equal to x squared. So then du on dx is 2x. So du is 2x dx. And now let's see, I've got a 2x dx, so that's equal to du. And I've got an x squared, and that's equal to u. So my integral becomes... So the 2x dx becomes a 1 du, and the root stays the same, and the x squared becomes a u, and I can do that. That is arc sine of u. Brilliant. But the u is really x squared. So not a trig substitution after all. One to watch out for. And I do not attempt to do that with trig substitution. I mean, you could. What you'd do is you'd go x squared equals sine u. And it would do the trick. In fact, it would do a very good job. But you should try to make it look like something that you know before you try trig substitution. So we've got another one. I could, I reckon, try... No, that's still an ordinary substitution. Right. Okay, so without the squared there, the outside is nearly the derivative of the inside, so an ordinary substitution would have done the trick. So it's the fact that that's an x squared is the real bugger here. This is going to probably be quite painful, but the message I want to send is how to choose what trig substitution to do. So we'll run with that. So what I would like, the philosophy of trig substitution, is first you just run through all your other options. And I mean, I could attempt to do this by parts, but it's not going to be fun, so I'm just not going to, yeah. So, because that half power, it's just going to get worse. So, all right. So our aim is to turn this into something that's squared, so that when we square root it, the squared disappears. And I know some things about functions that have identities, that have number minus something squared that turns into something else squared. That's how trig functions work. And so I need to come up with a trig function, a way of turning that into trig things so that it will do what I want. So here we go. I'm going to leave a space. And then I'm going to say, well, I know trig identities. That is the one most useful trig identity that I know. What I need to do is I need to find a trig identity that looks like this, where the 2 is a plain number that matches with the 1, and the bit with the x squared matches with one of these two. So I need to find something that has number minus variable squared equals variable squared. That's what I'm aiming for, because I need to turn this number minus variable squared into variable squared so that the square root will make the squared go away. So this does not currently look like that, but I can make it look like that very easily by moving the sign over here. Awesome. So look at this. Number minus variable squared equals variable squared. That's what I'm aiming for. My problem is that this number's wrong. I would prefer my number to be 2, because that is the number that is in my formula here. So I'm going to multiply everything by 2. Like that. So just to point out what I did, I started with the fundamental trig identity, I moved it around so that it was better shaped, and I multiplied everything by 2 so that the number matched this number here. So what I would like is for this to be equal to that. Because then 2 minus 3x squared will be 2 cos u squared. This is what I would like to happen. I would like this to be equal to 3x squared so that when I get my 2 minus 3x squared, it becomes a 2 cos u squared, and I can do the square root and the square will disappear. Okay, so I just declare that 3x squared is 2 sine u squared. Which means that when I do the square root of both sides, going backwards, I'll get root 3x equals root 2. And so that means that x is root 2 on root 3 sine u. So, now it looks like I just magically came up with it off the top of my head. So let x be equal to root 2 on root 3 sine u, and then root 3x is root 2 sine u, and therefore 3x squared is 2 sine u squared. Now cos u squared plus sine u squared is 1, which means that cos squared equals that, which means that 2 cos squared is that, which means that 2 cos squared u is equal to 2 minus root 3x squared, which means that root 2 cos u is actually equal to this. And that's great, because my whole point of this was to turn that annoying square root into something that is much, much simpler. There is a lesson to be learned here. Your working's not always written on the page in the order you thought of it. So it's good to put some space in to make sure that you can arrange for that to happen. Okay, so the decision that this had to be x equals root 2 on root 3 sine u was all based on where this trig identity went after doing about 6 lines of working. So I based my decision of which one on, I'm going to have to do this bit of the working anyway. I'm going to have to fiddle with the trig identities anyway, so I might as well do it first in order to figure out what the substitution would have to be. So I do this bit and go, oh, well, cool, that means that 2 sine u squared has to be 3x squared, so I'll put that back in here and work backwards to what the substitution actually is. So, now that I'm up to here, I have dealt with all of that. Tick. Okay, awesome. I've dealt with the root. Now I need to deal with the x squared and the dx, because everything has to turn into u. So let's see. I'll deal with the dx now. So recall that x was equal to root 2 on root 3 sine u, and so therefore dx on du was root 2 on root 3 cos u. So dx is actually root 2 on root 3 cos u du. Cool. So now I have dealt with the dx. Tick. Just have to deal with the x squared. But that's okay, because I knew to begin with that 3x squared was equal to 2 sine u squared. So we can do that. So, so also 3x squared equals 2 sine u squared. So in fact, x squared equals 2/3 of sine u. I could have just squared this one, of course, and gotten the same answer. So now I have dealt with the x squared. Everything's been dealt with. Each part of my integral is able to be replaced with something involving u. Let us see. So that's my original integral. The x squared is actually 2/3 of sine u squared. And the root 2 minus 3x squared is actually root 2 cos u. And the dx is actually root 2 on root 3 cos u du. Oh wow, and so I now have 2 times root 2 times root, that's 4 on 3 root 3 sine u squared cos u squared du, which I'm not at all happy about attempting to integrate. But I told you the goal was to try and get to this point. That is not fun. But I'm sure that there'll be some fabulous trig identities that will do the trick. Yep. There'll be 2 of them. So I'm going to stop here and pretend that I had a different question. It'd be so good in an exam, wouldn't it? Let's pretend that this is not the answer, and the answer is actually this. No, actually, it's not such a bad plan if you haven't got enough time to actually do the problem they've given you. You might possibly get like some marks. You've got to show that you know something. Just to point out what would have to happen at this stage, the fact that they're both even powered means that, like, if they were odd powered, I could pull off one of the sines or causes and do another substitution. But that probably means I could have done an ordinary substitution to begin with. So it's usually you don't need to do 2 substitutions if you've done it properly. And the fact they're both even means that my only hope is to use some trig identities. And so I do know that sine 2u is sine u cos u, and so what I have is sine 2u squared, roughly, except for the 3 root 3. And then, yeah, I'm just going to finish that off just a second. I'm just going to go as far as I feel I can cope with. So I know that sine 2u is 2 sine u cos u, which means that sine 2u squared is 4 sine u squared cos u squared. So awesome, I've got the 4 sine u squared cos u squared. I can replace that with sine 2u squared. But I still don't know how to integrate sine 2u squared, so I'll now have to use another trig identity, and I know that I can turn sine squared into cos 2 using the double angle formula. So I know that cos 2u is cos u squared minus sine u squared, and I need to just have a sine squared, so that will be 1 minus 2. What I've done there is I've replaced the cos squared with 1 minus sine squared. I'm not capable of remembering all 3 of the cos 2u formulas off the top of my head, so I have to get them from the first one. But I don't have sine u squared, I have sine 2u squared, so I'll replace the 2u with 2u and I'll get cos 4u is 1 minus 2 sine 2u squared. And then I'll rearrange that to get the sine 2u squared again. So we've got, that goes over there, 2 sine 2u. Sine 2u squared is 1 minus cos 4u, and so sine 2u squared is actually a half minus a half of cos 4u. Awesome. So what we actually have is a 3 root 3 in there, so I might as well put, so actually this sine 2u squared is the 4 sine u, cos u 4. Sine u squared, cos u squared is actually this, and therefore 4 on 3 root 3 sine u squared cos u squared is actually sweet, great, and so therefore my integral actually is the integral of this. Because all of the stuff inside my integral came out to this answer here. And now I can finally integrate it. So this is just a number, so it'll attach a u to itself. And the 1 on 6 root 3 will still be there. The cos will go up to sine, but I'll have to divide by the 4 plus c. And the really distressing bit is now I need to know what sine 4u is in terms of x. So I have to use even more trig identities to figure out what that is, and I'm going to stop there. But you know, they would not give you something that was this horrifying in the exam. Yes?
Could you convert the sine u squared into 1 take cos u squared?
So the question is the sine u squared, like way back, here, convert that sine squared into 1 minus cos squared? Yeah. Yep, that's a good plan. But what we'll end up with then is a cos squared and a cos to the 4. And the best plan for dealing with those would be a reduction formula, which is not worse than this. Okay, so, and the advantage of the reduction formula in that sense is that you actually do know what cos u is, because we wrote it back here. Cos u is actually this divided by root 2. So there's a certain advantage in that. But what will actually happen in your exam is most likely, if they give you a trig substitution, what you will end up at this stage with is it's likely not to have the squares. And you'll just go, oh, well, I can do a sine 2u there. Or it'll just have one of them with a square, like it'll just have sine squared, in which case you'll use this trig identity and turn it into a cos 2u. So it's much more likely to not be this horrifying. But I just wanted to point out a few useful things about choosing what goes where. Just a couple of points about the choosing what goes where. If you had a plus, then the trig identity with number plus function is not this one, because this is function plus function. So you're going to have to divide everything by cos squared and get 1 plus tan squared equals sec squared. So what if we had something like this? We had that. So we could go like cos u squared plus sine u squared equals 1. That's not helpful because we want number plus variable, and we have variable plus variable, and so that's not going to help. And so we need a trig identity that has number plus variable. So if we divide everything by cos squared, we'll get 1 plus tan squared equals sec squared. And so now we have number plus variable. So you could then eventually get like 2 tan u squared is 3x squared. Alternatively, instead of using a trig substitution, you could do a hyperbolic trig substitution. In which case we can get which is kind of nice. So now we have number plus variable, which is what we had. We'll times everything by 2. And we want that to be equal to this. And so you'll say that 3x squared is 2 sine u squared. So that is an alternative. The problem with hyperbolic trig is that you have to know all of your matching hyperbolic trig identities later. So you're going to usually have to use, you're going to eventually have to use the fact that cosh 2u is cosh u squared plus sine u squared, which is 1 plus 2 sine u squared and two cosh u squared minus 1. So you'll eventually have to use one of those probably if you use a trig, hyperbolic trig. So I'll see what I did there. Cos 2u is cos squared minus sine squared. Cosh 2u is cosh squared plus sine squared. And then you replace the sine squared, you replace the cosh squared with 1 plus sine squared and you get this. Or you replace the sine squared with cosh squared minus 1, which means you get this. So, yes. Basically, they're the same as the ones for cos, but with the minuses in other spots. Actually, the one for cosh at the end, the cosh 2u and the cosh squared u is the same, interestingly. But that's a coincidence. All right. That's probably quite enough trig identity, trig substitution-ish. There are more examples of it in the other revision seminars. I believe there's a revision seminar specifically on trig substitution if you want to watch more of them. And yes, there's always your lectures. You can watch them again to see how your lecturer goes about it. Cool. There is one on eigenstuff as well. And please go and have a look. There's revision seminars that cover pretty much everything in Maths 1A on the website. I'll let you know, I'll email you when the videos from today are ready. Thank you.